In the last video, I showed three methods to calculate an integral. I want to compare these methods a bit. This video will try to answer three questions. First, for the task of only calculating the integral, which method is the best method? Second, do we get anything else except the integral? And third, how well are these methods generalized to 2-dimension or 3 or more dimensions? So for the task of only calculating the integral, which method is actually the best? Well, the Riemann sum is probably the most accurate method of the three, and probably the fastest one as well if you compare the same amount of points. I am basing this on my own experience in 1 dimension, 2 dimension, and 3 dimension, but I could be wrong for higher dimensions. Anyway, again, the Riemann sum is only more accurate and more fast if you compare the same amount of points. But rejection and importance sampling can actually give you pretty good approximations with much less points than the Riemann sum. So I would say if you only care about accuracy, then the Riemann sum is probably the most accurate method. But if you care about execution time, then rejection and importance sampling can be also good. But there's one condition. The condition is that the proposed distribution, for the rejection sampling, it's the distribution that you use to bound the actual function that you care about. And for importance sampling is the easy distribution that you draw samples from. So these proposed distribution have to be close to the actual function. If they are not close, then actually these methods will not be so fast as the Riemann sum. And I really want to show you this in action. Okay, remember that in rejection sampling, there's a point where we draw from a uniform distribution between 0 and 1. And this distribution, this 0 and 1, corresponds to this area over here, where this is 1 and this is 0. It corresponds to, you could say, the y-axis in this graph. But for the second graph, for the second proposed distribution, it will correspond only to this. This will be 1 and this will be 0. So you can see that for the upper graph, most points, let's say we drew 5 points that all came minus 1.1 but had different results in the uniform distribution. So it could be that we got 1 point here, 1 point here, 1 point here, 1 point here, and 1 point here. Notice that only these 2 points will be accepted and these 3 points will be rejected. Whereas in the second graph, if we had the same thing, if we drew 5 points from the same point, then we would get something like this. And notice that here, 4 points will get accepted and only 1 point will get rejected. So rejection sampling can be very, very wasteful of the points that you draw if you are not careful to have a proposed distribution that fits the actual function that you are trying to calculate. We can see this also in the ratio. So for rejection sampling with a uniform distribution, we get that the ratio is 0.18, but for the normal distribution, we get that the ratio is 0.695, which is a lot higher. So in rejection sampling with a proposed uniform distribution, we threw away around 82% of our points, whereas in a normal proposed distribution, we threw away only around 30% of our points. Okay, so the second question was, what do we actually get from running each method? So in the numerical, in the Riemann sum method, all we get is the integral. We don't get anything else. In rejection sampling, we also get a sample from the posterior distribution. So you can see that the sample of accepted points actually looks like the posterior distribution that we were trying to sample from. And this also goes for here. Now, having a sample of the posterior in Bayesian statistics can be much more valuable for your analysis than the normalizing constant. By having a sample of the posterior, you can calculate credible intervals numerically, you can use it for hierarchical models, etc. Now, in importance sampling, it seems that we also only get an integral, but you can also use importance sampling to find mean, variance, and other quantities of interest. I will show now how to find the mean. Now remember that the mean is an integral over x, p of x, dx, and that p of x is actually our unnormalized posterior divided by the normalizing constant. Okay, and we can write this like this. Now we can use the importance sampling trick on both the numerator and the denominator. And again, we can look at this as if we are drawing from this distribution, the proposed distribution, and calculating some quantity of interest. So we can look at this as if it's the mean of this quantity divided by the mean, according to g of x, of this quantity. And we can estimate this by the sample average, which will be when our xi's are drawn from g of x. And these two cancel out. And this is exactly what we calculated in the last video, and this is just also possible to calculate pretty easily. And then you just divide the two and you get an approximation of the mean. Now, in addition, these weights, these f of x's divided by g of x's, they can actually be used to help us sample from the posterior in what is called sampling importance resampling, or SIR, or SIR, and I will make a video on this soon. Okay, so the third question was, how does this generalize to 2-dimension or 3-dimension? And you can see that it generalizes pretty well. The Riemann sum, well, let's say that this is our function over here, yeah, this dome over here is our function, and we use columns, but now these times these columns are in 3 dimensions. And the smaller the columns, the better approximation we get from a Riemann sum. And we can see this in R. Let me clean this. We have a function, and this time the function has 2 variables. Yeah, it's e to the power of minus x squared minus y squared. And this time we need the intervals to be both on the x-axis and the y-axis. And we need to create a grid of values for the x and y. And this function over here helps us to create this grid. And for each value in this grid, we calculate the value of the function. And then we just sum over all the values of the function and multiply that by the length of the intervals. And notice that this time we have to multiply it by both intervals. Yeah, so if we do this, if we do this, we get that the integral sum up to pi, which is the actual value of the integral. And this is the same in rejection sampling. If we use the, let's say, the normal distribution as the proposed distribution, we sample from a multivariate normal centered around 0, 0. The bounding constant is 2 pi in this case. We calculate the ratio. We draw from a uniform distribution between 0 and 1. We calculate which points we accept and which points we don't accept. And then we calculate the ratio of all the points that we accepted to all of the points. We can see that in this case, it was 0.5, so half of the points we accepted. And then we just multiply the ratio times the bounding constant. And we can see we, again, get pi. And in importance sampling, it's also the same. You draw from an easy distribution, from a proposed distribution. Again, we can use the multivariate normal. We then calculate the weights for all of these points, and then we calculate the mean of those weights, and you can see again we get something very close to pi. I will leave a link in the video description for both this script and a script I made for 3 dimensions, which is something that is pretty hard to visualize. And that's all I wanted to show in this video. In the next videos I will show how to find the bounding constant, this thing over here. Yeah, the bounding constant, how to find it, and also how to use the weights in importance sampling, these things over here, how to use them to actually sample from the posterior distribution. So thanks for watching.